Electronics 1, Kirchhoff law, the Thevians and Norton theorems, Eugenie E. McEval, the College William and Mary, week 2. Kirchhoff's current law of the algebraic sum of the currents entering the existing of a node equals zero with the convention of the quite arbitrary with the currents getting the node with the positive. This one goes out with the node of the negative. Kirchhoff voltage law with the algebraic sum of all the voltage chain with the voltage drop in a loop with the equals zero with the node. Choose the direction along with the travel of the network. If you go over the resistor, current runs the same way the voltage chain with the negative, otherwise positive. If you go over the voltage or over the negative, the terminal to a positive voltage changes in positive with the otherwise negative. Our goal is to find the divided by 1, divided by 2, and divided by 3 voltage at A is equal to 0 for node A over 1 minus 1 over 2 minus over 3 equals 0. We need two more independent equations. For this, we'll go over small loops indicated. So we have voltage DC over voltage CA over voltage AD equals 0, voltage A over B over plus voltage BC plus voltage CA equal to 0, and then we notice that. Here's another look. Maple is math aid. Thevian's Norton equivalent circuit theorems, any combination voltage source, current source, resistors, two terminals, electrical equivalent. Thevian's theorem, single voltage Thevian is in a single series, a resistor Thevian connected in series. On the left, Norton's theorem, a single current source of the Ampere Norton, single series resistor Norton connected in parallel. No above circles are equivalent to each other. So we have a voltage Thevian, battery resistor Thevian, and then we have a current source, amperes Norton, resistor Norton. Note above circles are equivalent to each other. Resistor Thornton is equal to resistor Newton, and amp Norton is equal to voltage theorem over the resistance theorem. Thevians. Chapter 2, Kirchhoff law and Thevian's theorem. Chapter 2, Kirchhoff law and Thevian's theorem. In this course, we'll use a variety of mathematical conceptual with logic with the descriptive electrical component of the circuit with the Whitwell encounter with the Ohm's law avoided the first such model. This chapter will consolidate some of the concept of the last week with the general model with a linear device known as the Thevian equivalent device, the input impedance, the output impedance of the internal voltage. The Thevian equivalence will be generalized using the described properties of the signal. The signal will describe not only with the voltage but also with the output impedance of the difference of the transfer over the concept of the impedance over the signal that you external sensibly through this work will discover the various methods of the form per property of the signal. But this week we'll examine the network and know the complete framework known as the Kirchhoff law. The rules will also use the analyze the property of the combination of resistors and power supply. Kirchhoff law if the connect with the power supply with the resistor of the consolidated network within the current flow through all the various elements of the ensure the change charge is the conservative energy is conservative the Ohm's law satisfies to each with the resistor simultaneously satisfying all of the conditions will give you the exact one solution. Method of the writing down the solution representative of the conservation law with the Kirchhoff law with the explore with the least law with the will consider sample the circuit shown in figure 2.1 a circuit with 2 power supply and 3 resistors. Kirchhoff's point of law, but the Kirchhoff point of law says that all of the current flows to the junction would come out of the junction with this mean with the charge of the conservative with the more favorable the circuits or loops. Any action the concept is illustrated from the junction with the example circuit is figure 2.2, and in this case inductor 1 plus inductor 2 minus inductor 3 is equal to 0 for the choice of the current with the direction sample circuits. Voltage capacitor 1 and 2, the amperes inductions also look like resistors sometimes, and there's 2 of those going into the ground 3. Alright, note the signs of the convection will say with the current positive defined with the flow of the junction, negative defined flow of the junction. Kirchhoff loop's law says that if you sum of the voltage around the closed loop of the circuit with the total must zero with the percent of the voltage drop, the representative energy per unit of the charge with the mean of the energy which come with out of the circuit with the heating of the resistor with the example that's most come from some power of the source, such as power supply, but this is just the conservation. The single convention of the voltage increase with the current of the power supply, but the decrease with the resistance direction of the flow. The direction of the current flow should be the same as one defined with the point of law. With an example, one of the circuit that has 3 loops can be considered as shown in figure 2.3. Above these 3 loops were obtained with the following relationships. 0 is equal to voltage 1 minus amplitude 1 over the resistor 1 plus amplitude 2 over the resistor 2 divided by the volt 2. Minus the volt 2. 0 is equal to voltage 1 over the minus amp 1 times resistor 1 minus amp 3 over times resistor 3. 0 is equal to voltage 2 with minus amp 2 with times resistor 2 minus amp 3 times resistor 3. And two relationships of a single 3 are not independent of the point of the relationship between the 12 of the current with each of the resistor, hence with the power of each of the resistor. Be it a real nightmare to solve with the complicated networks we develop with the models and methods to avoid the term complicated networks whenever we can. We'll usually make this part of the circuit relatively independent with another with the most commonly Kirchhoff laws. We'll usually say with the voltage input with the resistance with the voltage is equal to the amp, the resistance, or the amp ohms applied with a simple relation with the resistor connected with the tree. With its next section, we will begin to explore how it is possible. The Thevenin equivalent. Thevenin equivalents are modeled to describe the input-output property of the device. It will assume what the input of the device looks like. Of the resistor of the other end of the ground, connected ground will assume what the output looks like an ideal voltage shown with the resistor, but those are shown in figure 2.4 with the low with the note that for this week's discussion, term resistance and impedance tree with its anonymously. One of the determinative input is impedance is Zin base input. Input impedance Zin. Simply applying voltage to the input, measuring the current flow of the device, and applying Ohm's law. So we have input voltage impedance. Input impedance equal to the ground, voltage Thevenin to voltage Thevenin device, and then output. Thevenin equivalent circuit for the input device, and the right with the Thevenin equivalent voltage circuit given in any electrical device with the two output terminals will assume the one is called for the ground with the number that you might do to try to determine the property measure of the voltage curve of the terminal attached to the resistor of the terminal measure of the voltage change the resistor measure of the voltage. Again, repeat clearly all the variations, simple measurement of what is for the minimum number of the measurements you do with the character of the black box completely. Thevenin answer just 2. Thevenin theorem in a linear over the ohmic system of the two terminals can be completely characterized as ideal voltage Thevenin voltage in series with one resistor Thevenin resistance also cover the internal resistance. Sometimes don't matter what the resistance load you connected across the two terminals and form the voltage divider as shown in figure 2.5 on the right. Some of the voltage across the load resistors given by the voltage load equal to the voltage Thevenin times the resistor load over the input impedance time plus the resistance load. It's a special case where there's any load applied with the option above with the resistant load that is an infinity of the output with a simple voltage Thevenin, and for the result of the two measurements called the resistance Thevenin, and figure 2.5 show the voltage of the connected load can be treated in voltage divider. Voltage divider and Thevenin device loads. Consider the habits of one voltage divider for the last week with we connect with the load resistance to the output for the last week with the compute with the output of the load voltage divider was given by voltage load with voltage input over time for the resistance 2 with over resistor 1 times plus resistor 2 with times resistor load time over the resistor 1 parallel with resistor 2 plus resistor load. With the equal effect of the relation for the one with the previous section, you can see that the loaded voltage produced the Thevenin equation. Voltage Thevenin is equal to voltage input over the resistor 2 over the resistor 1 plus 2, and voltage Thevenin is equal to resistor 1 and 2 parallel equal to the resistor 1 times resistor 2 over the resistor 1 plus resistor 2. Relationship of the Thevenin makes sense with the simply unload with the output voltage that described in the previous section, and the output impedance is similarly parallel with the equivalent to resistor with the voltage divider. Design stiff voltage divider. A stiff voltage output implied with the output voltage stay with relative to the clip with the Thevenin or unloaded rule when it's loaded and implied with the rule of thumb in the designing with a stiff voltage source of the output should not deviate with more than 10% when loaded. From the relation previous section, we can see that the implied with the load resistance must be more in fact within 10 times larger output impedance than the voltage divided with the voltage. The resistor Thevenin is equal to the resistor 1 and 2 parallel. You can think of the rule of 10. We easily with the design of the resistor 1 itself is smaller than expected load by a factor of 10. General application of the rule of 10 notable. Since we are again going to design construction some more very complicated circuits this year with the needed apples with a focus with a part of circuits which call the sub-circuit for the example the alpha the bill of the amplifier 3 stage of the basic idea is always ensure downstream elbow that do not load upstream of the elements of one of the first stage with will buffer the amplifier take the single amplifier with the current with not the voltage of the alive with the connect with the next probe with the amplifier without change the loading characteristic whenever the generated is single with the second stage will be voltage amplifier signal voltage whatever level that we need the final stage will be another buffer amplifier that again amplified with the current so that we will not load or voltage amplifier that was in output but the gains the two major advantages will never the large number of the independent simultaneously equations to solve that our circuits will be under the wide range of different operational conditions. Here are the general procedures. Any subcircuit that can be modeled with the Thevenin theorem is an ideal voltage source and in series with the resistance voltage theorem. Resistant Thevenin. In the connection with the next subcircuit with the we can represent with the load resistant load with the making the voltage divider. We can keep our equation simple that neither the employ with the full Kirchhoff law formalize simple the following factor of 10 rule. In summary, anything that we design to produce the reliable voltage should be with the resistance Thevenin smaller than the resistance load by at least a factor of the 10 that do not want the voltage to change significantly with the subcircuit with the subsequent parts of the circuit. Consequently, voltage sources. Constant voltage sources. The most common subcircuit that will be used to supply with the voltage later part of the circuit with the power supply with the power with the other subcircuit that may be the biasing network to keep the transistor in normal operation region with the type of the subcircuit with the voltage output relative to the input with the resistance load with the means of the input impedance so that it means the resistance load is greater than 10 times resistant Thevenin. Constant current sources. Constant current sources we later see with the transistor the current amplifier but the means often we want to drive the amplifier with the current source. The current source can also be modeled with the ideal voltage theory with the resistant Thevenin in a complete circuit that will look like the ideal voltage source driving voltage divider, but we want a current with the resistance and impedance to be the relative independent of the resistance impedance. This means we want the same current that we remove the input impedance just connect with the short with the two together leads together and applying the same logic above the resistant load equal to 10 times the resistant Thevenin and a stiff current source. Resistant load is less than 10 times resistant Thevenin and a stiff current course. Impedance matching. There are two cases where resistant load equals the resistant Thevenin. We'll call this impedance matching. Once most of the effective transistor power to your load, then must achieve the resistant load equal to the resistant Thevenin. The most equivalent efficient transfer we can make is ampere squared times resistant input impedance equal to the voltage input over the resistor's impedance times resistor Thevenin to the square root of 2 times resistor input impedance. If the largest value of the resistor load, if the resistant Thevenin, of course, several loads of the source are dropping the output voltage exactly for a factor of 2. This may, however, be with a fine simple trick with the lighting a light bulb, the driving the audio speaker with the second cable with the 1 amp fast signal with traveling along transmission stuff with the BNC cables. We often use the connecting laboratory equipment, then we want to prevent reflections or connections such that these could give phony signals that they want you to achieve with the resistant load with the resistant Thevenin and those with the decrease the amplitude of the signal accomplished with the attaching 50 ohms terminator to the end of the BNC cable to ensure the impedances match. Design exercise shows a used Kirchhoff law during a Wheatstone bridge depicted in figure 263. So they have a resistant Wheatstone bridge circuit. Find relation voltage output, amp output, resistant impedance Thevenin does not depend on resistant load Thevenin equivalent circuits on the right. How to measure Thevenin, measure resistant voltage power supply. Prove the power transformer power supply Thevenin resistant Thevenin is the resistor load and maximum resistant Thevenin. Alright, lab.